Good afternoon, everybody. Today we'll have our part two of design of post-tension concrete floor systems. I understand that a good number of you did not attend the first part, so the notes will be available for you, which covered actually the main things on post-tension floors and flexural design, and also there's a good number of examples also at the end of the slides of part one. So you should have access to that as well. And if there are any questions, of course, you can email me at my email, which is at the end of the in the last slide. So today we will continue with our discussion. We have a good amount of slides to cover. So we'll get started. So last time we talked about flexural design and shear design. After we made an introduction about PT slabs and the basic principles of doing that. So one of the main issues when we are designing PT floors is punching shear. So and actually many buildings collapsed during earthquakes in particular due to punching shear. So I assume you are familiar with this from concrete design. So we will talk about I'll talk about that in general, and then we'll talk about what's related to PT floors, what's different, which is not much, and then you will have an example on that you can go through. So basically, we're following the ACI procedure, which is based on tests and many tests that were done in multiple universities in the US and Canada. So the calculations for punching shear is as follows. So basically, we need to determine what is the applied moment, mu, and what is the applied shear on the slab. Those are taken from load calculations or are taken from the models. If you have a structural model using any software, and then we consider for the design moment, we consider a fracture for the shear for the imbalance moment, which is gamma V times mu. And as you know, from reinforced concrete, we have the same thing. We have also gamma F times mu, which is used for flexural design. So here it's very important that we don't consider only the shear force on the slab, but we also have to consider the unbalanced moment. So based on this, we can, using the chord relationships, we can select the assumed failure surface, which is the critical section that typically at the distance d/2 from the face of the column. And then we can determine the critical area and then determine the shear resistance of the concrete floor. So this is true for PT and true for reinforced. So we do the check. For reinforced concrete for the concrete itself, and if the allowable capacity is exceeded, then we have to do we have to provide shear reinforcement. Okay, and the shear reinforcement could be in different ways, which is could be stirrups, could be stud rails as well. They are both allowed by ACI, and if, of course, that doesn't work for the applied load, then we have to make some changes to our design, such as column dimensions, slab thickness, concrete strength, also increase F prime C. So these are the main things that will affect the design capacity of the slab. Okay, the slab thickness, the concrete strength, or the column dimensions. In addition, of course, to the shear reinforcement that we provided. But once we Once that doesn't work with reinforcement, then we have to increase one of these parameters. So this figure shows um, like an interior column, an edge column, and a corner column, showing the critical cross section that we need to consider for punching shear. So based on that, as you can see, typically we have the largest area of shear resistance is in the interior column, because the critical section, that's the dashed line which goes around the column, and then for an edge column it's 3 lines only, and if it's a corner column it's 2 lines only. So typically we have to be careful about punching shear in corner columns and in also um, edge columns. Okay, so here, so the procedure is exactly the same as reinforced concrete. Okay, the only difference here, so here you have a detailed example that you can go through. It's a step by step, but for the sake of time, so we have about 200 slides. For the sake of time, I'll go through it quickly. Um, so basically, this is the given data, including the strands that we have for PT. So this is the arrangement. Of course, everything is given after designing for flexure and everything. So we can see the arrangement of the tendons and the arrangement of the reinforcement, above the column. So as you can see here, we have 8 number 4, 8 number 4 in each direction at the top. And then we have to check that. So here we have those are given, the unbalanced moment in both directions. In the x direction, the y direction are given, and then the ultimate shear is given. Those are from the analysis. Then we have to determine the critical cross section, which is at the distance d/2 from the face of the column. Then we can check the stress. So once we have the loads, we need to check the stress. That's the applied shear divided by the area of the critical section, and then the unbalanced moment, that's gamma v times mu times c divided by j. Okay, and those are, of course, given values here. And j can be calculated, as we'll see also. So we need to calculate that. So all the values here are calculated, as you can see. And then this is the stress due to the unbalanced moment in punching shear. So we check these stresses and then we compare them to the allowable stress, which is given by this ACI equation. So here, this is the concrete capacity, but it has the contribution of the post-tensioning force in the cables. So here we have that FPC, so which is typically, we can assume a value like this, that's it's 125 psi start from that, but this has to, of course, be, this is taken from the flexural design, knowing how many cables we have in the slab. And then we have VP, which is the component, the vertical component of the PT force, which helps. So in reinforced concrete, we don't have the VP and we don't have the 0.3 FPC. So as you can see, if in PT slabs, we have an advantage by having this contribution to the shear capacity of the concrete, because also this is typically PT floors are considered uncracked according to ACI code. So that helps. So we calculate this, and then we can compare that with the allowable capacities. And then we check that with the maximum shear allowable. So that's the maximum that's given by ACI. Okay, so that's greater than what we have. So this is okay. If this is not, then we have to change either the concrete strength or the slab thickness. In particular, typically we play with these, the slab thickness or the concrete strength. The first thing I would start with is increase the concrete strength, okay? If that doesn't work, then maybe we have to increase the slab thickness as well. But typically the last thing is maybe changing the design, changing the dimensions of the columns, okay? So then, okay, according to what we have, we need the shear reinforcement. So we calculate the shear reinforcement with the minimum. This is exactly similar to reinforced concrete. The only difference here is that here we have when shear reinforcement is provided, then this limit is instead of phi 2 lambda f prime c, then we have phi 3 lambda f prime c, and this is because we will be using stud rails. Okay, if we are using stirrups, then it will be phi 2 lambda times square root f prime c. So we continue with this, uh, and then we design the amount of shear studs that is required based on the shear area that's required here, which is 2.23. Okay, so based on that, we select the number of rails in each side, and then the number of sides we have 4, so that would be different if you have a corner or an edge column. Then the number of slides is the studs, sorry, is the total area divided by the area of each stud. Then we have that, and then the distance between the studs is calculated. So we have 3.3 inches, and then now we check the shear stress in the parameter outside the shear reinforcement. Okay, and then this has to satisfy. That's when we stop adding studs. So so this is the arrangement that we will typically have. So based on this, we'll have 10 studs at 3.35 inches if it's unbonded, and if it's a bonded tendon, we have also the same thing. Okay, so that's an example. You can go through with the numbers in detail. Next is we will have the deflection. um, Deflection is another important parameter in the design of concrete slabs in general, not only PT, but in PT it's easier, okay, according to ACI, not other international codes. For those of you who are designing structures outside the US, the reason is because the ACI code, the ACI code requires the PT floors to be designed as uncracked. Okay, the U class, we call it the U class, which we talked about that in the first part. Um, so in that case, then if the slab is not if the class is uncracked, then this is easy to calculate the deflection. The section is uncracked. Okay, so you're familiar with deflection calculations of beams from reinforced concrete design, but this is when it comes to slab, it's a little bit more complicated because it's a slab, it's not a beam. So here for the slabs, typically, um, uh, we have a plate that we need to check the deflection for. So it's not simple. So we have different methods that we will talk about that can be used to determine the deflection. And these days, of course, we all use computer programs. So most computer programs, they give you the start, right? Not everything, but the start on how to do that. Okay, and of course some simplified methods. So typically we use a deflection index D/L, which depends on the span, typically in the vertical offset from the zero line to determine that. So this is typically the method that we use, but I mean, typically that's not it's not accurate, sometimes, because it's a slab, so we may have deflection in both coming from both sides if it's a two-way slab. So we have to be careful about how we look at that. So we have the term that's called the notional span. So it's not actually the real span, but it's the notional span and the vertical offset D from the datum line. So here you can see what I mean here by by when we look at the slab. So we don't have to be very conservative in our design. So it's evaluated in such a way. So as you can see in figure A, we see the L distance, okay? But the datum line, you can see how the datum line it's inclined. So we measure from that line, okay, typically. Okay, so again, as I said, the span is not a straightforward like term in the deflection calculations. Okay. So it's of course the floor deflection is very important, and And this is another important design parameter. In addition, after we design the slab for flexure, so that's what we do. We design it for flexure, we design it for bending, flexure and shear, and then we check the deflection. But keep in mind that the initial selection of the slab thickness is based on L over a value, right? L over 45, L over 48. We talked about that in part one. So there's a table in the notes of part one that tells you what you need to use, L over what, for a PT floor. Okay, L over what. So you start from there, so that helps actually sometimes in eliminating even deflection problems, because things may work for flexure and shear but may not work for deflection. Okay, so damage may occur if damage may occur to the slab, and also to what the slab is supporting, like mechanical MEP components, architectural components on the floor, and it will not be comfortable, of course, for the occupants, of that floor. So typically, the vertical out of level to span ratio is 1 over 250. Cantilevers is 1 over 125. ACI recommends L over 240. Okay, and then deflection damage to mitigate damage to non-structural component is L over 480. So that's very stringent. Okay, that's very stringent if we don't want any damage to the non-structural components. Okay, so deflection limits to mitigate malfunction depend on specific functions. For drainage, ponding, proper operations of doors, shelving, 1 over 250 or L over 250 is generally used. Okay, so that's what we typically use sometimes. But if there are strict requirements, especially if there's like an equipment in a hospital building, for example, then we have to be careful about the deflection limit that we have to use for the design of these floors. So so we start typically by evaluating elastic deflection, but that increases, of course, non-linearly due to creep and shrinkage, okay, which we are familiar with from reinforced concrete. So it's the same thing. So these are time-dependent deflections that we have to consider. So typically in the design of concrete slabs, we start with we start by um, elastic deflections, and then we multiply that by a factor to determine the long-term deflection, and which we will talk about, and that's basically it. That's how we do it. But sometimes we have to do detailed analysis of concrete floors, and I've done that in actual projects, considering the spans, that we have. Okay. So, so basically, the calculation methods that are used typically, there's closed form solution formulas or tables for uncracked sections. Those are based on elastic analysis. The strip method using linear elastic response, um, um, uh, um, and also no cracking. There's the strip method using linear elastic response and allowance for cracking, and also an average equivalent moment of inertia. So we did the equivalent moment of inertia. We did that in reinforced concrete design for beams. But again, here, since we're talking about plate, so plate theory have to be used here. Then there's the strip method using linear elastic response, and then allowance for cracking and local equivalent moment of inertia combined with numerical integration. That's a little bit more complicated than the previous one. And then there's modeling of the entire floor using finite element-based programs using linear elastic analysis with no cracking. So we do that every day in the offices. We do that every day. So when you design it, then we check deflection, then we look at that deflection is based on linear elastic analysis with no cracking. Okay, now this can be modified. Okay, can be modified to allow for cracking by providing a factor to the moment of inertia. For those of you who use RAM concept, for those of you who use SAFE for the design of concrete floors, that's typically what we do. Okay. Now, all these procedures are used. But if we look at the results, for example, if we look at an example like this, of course, we're not going to go through each method because the solution of each method for the plate is really difficult. So this will require actually a long lecture by itself looking at that. And there's ACI 435. ACI 435, which talks about deflection calculations in concrete members. But if we are looking at the floor like this, and then taking a panel and then looking at that, this is the given information for the slab thickness, column sizes, and the base size, and the concrete that we're using 5,000 psi. It's a normal with concrete, and modes of elasticity is calculated, and the steel is also known, the superimposed load, the live load, everything is given. So for the immediate deflection, we calculate dead load plus live load. Okay, and then here it goes by like method by method. Okay, I'll show you the result that were obtained using method by method, and then you can see the difference in the deflection calculations. But and then we'll talk about PT slabs. But again, this is general for all concrete floors. So we have closed form solutions. We have tables. We have tables that we use to determine the deflection. Or for those of you who have Works formula book, which has a lot of closed form solution equations, there's one chapter for plates that can be used, which includes these coefficients depending on the boundary condition, if it's like fixed or fixed pinned or fixed free, etc. Okay, and then we calculate based on the ratio between A and B, the sides of the slab. We can determine the the coefficients, and then we can use this equation to determine the deflection of the slab. So that was determined using this simple method, using these coefficients and this equation. And then there's the strip method using linear elastic and no cracking. Again, this requires detailed analysis, and it's a very good method, the strip method, and it's used also with allowance of cracking. So by dividing the slab into strips, so we can look at that like a beam basically. But here, as you can see, there's deflection from both sides. So we have to consider the total deflection that's coming from this side and that's coming from the other side. Okay, so this is basically the how we divide, how we take a strip and check the deflection, based on that. Okay, so using this, we determine what is the deflection that we have at the center of the panel. And then method 3, this is allowing cracking, so we have to determine the effective moment of inertia. Okay, so this is again with cracked section. So you can see here in this area where the cracked moment has been exceeded, so we don't have all the area of the cross section effective in resisting the load, in resisting the deflection, or even the load. Actually, that's correct for flexural design, because part of the concrete resisting, and then part of that is the steel and the tendons are resisting. So we use this procedure from ACI that we use for reinforced concrete slab. It's the same. And then we calculate the average effective moment of inertia, just like we do for reinforced concrete slab. And then we determine that to be 0.53 inches, which is more than what we got before. And then this one is the linear elastic strip method with linear elastic allowance for cracking and combined with average effective moment of inertia. Okay. So again, this is actually iterative procedures that we can use, and then modeling, which is something that we do every day, and we can get the contours like this to determine the deflection and look at the maximum deflection. So when we do this, actually, we can use this method here, finite element, and then look at the elastic deflection and multiply it by a factor. Okay, in many cases we use 3. Sometimes we use 2. Okay, so it depends. If we want to be conservative, really, it's 3. But in some cases, for long span slabs, it could be more 3 if we use detailed analysis, which are available in some of the computer programs. Okay, and then here modeling of the entire system using finite element and allowance for cracking. This can be done in the same model, but we reduce the moment of inertia, because as you can see, the moment of inertia here is less. Okay, because it's a cracked section. Okay, it's a cracked section, so it's less. So we have to use a smaller section. Typically, we use 0.25. So that's a lot of reduction in the moment of inertia. Now, looking at the comparison of the six methods, you can see the difference in the in the deflection. Okay, so it's important to, for any method that you use, you know its limitation. Okay, so if it's linear elastic, no cracking. If it's linear elastic with the cracking, so when you do any adjustments, you do it right. Okay, for creep and shrinkage, because they are time dependent long term. Okay, now for for post tension floor systems, we have either do not crack under service conditions, that's uncracked, and crack to a certain extent, but does not invalidate the calculations based on the gross section. So there's some cracking, but we can still use gross cross section. So that's important here. Now, since ACI it has like small allowable or low allowable tensile stress limits, typically it comes to be like uncracked. So unlike, for example, Eurocode 2 or other codes, so we can use actually the uncracked section, for that. Okay, so this will be very simple. In that case, we have there are two cases to consider for the live load. Uncracked member, that single solution for like one times the live load, and then for the cracked member, then we have dead load plus live load. That's the first solution. Then the second solution, we use the load combination of dead load, and then the live load combination is U1 minus U2. So U1, which is the dead load plus the live load in the first case, and then for the second solution, for the live load combination, we use U1 minus U2 because the section has cracked already after, under the dead load. So for the live load, we have to take that into consideration. So this shows the the load deflection curve and how it changes from uncracked to uncracked, and it took uncracked to cracked. And you can see the difference. You can see the difference between, if we consider it uncracked, that uh, uh, that curve at the beginning will continue straight if this is uncracked, okay, theoretically. But since the concrete will crack after a certain point, it will follow that, and we can see the difference will be really, really high between both. So one way for the long-term deflection, which applies also to PT, is basically we calculate the instantaneous deflection based on uncracked section, and then we multiply that by a factor, okay, to obtain the live load. To obtain the long-term deflection. So that's basically the simplest way to do it. And here we have that factor. It depends on like the duration, and you can see most of that will happen in the first 5 years, the first 60 months, and then it will stabilize relatively after that. So you can see here it's less than 2 after 5 years. Okay, less than 2 after 5 years, but most of the long-term deflection will happen during the first 5 years. Okay, so that's why sometimes when we use a factor of 3, that should be enough for typical applications. Okay, so for PT, then the simplest conservative first estimate load combinations for long-term deflection, we have 1 times the self-weight plus 1 times the superimposed dead load plus 1 times the post-tensioning force plus 0.3 times the live load times that factor. Okay, the long-term deflection multiplier. Okay, and here we have the percentage of shows the percentage of final shrinkage and creep shortening that will happen during the first 25 years of the structure. So typically we will reach creep and shrinkage will happen during the will achieved 100% after 25 years of the structure's life. Okay, so that's for deflection. Now we'll talk about the anchorage. We'll talk about the anchorage zone design in post-tension floors. So um, as we know, we have to anchor. We have to anchor the PT at the ends. Okay, we have to anchor the PT at the ends, and then that's where we apply the post-tensioning force. So for that, for that, we have a high force applied at the end of the member, okay, at the end of the slab. And sometimes, of course, if it's a PT beam, it's the same concept. So here we have a large force applied. Here there are two things that we need to look at. There is the local area, which is very close to the where the force is applied, and here the top figure shows the local area. So you can see here high compressive stresses applied, and then we have high tension stresses applied, and then it will stabilize and it will become uniform load after that. So that's for the local area. For the general area, as you can see below, so we have the force apply. You can see how the stresses would happen here. And then after a certain distance, they will stabilize. And then we will have uniform compression after that. And that's the goal of the PT, having more compression force in the slab to prevent of course, the tensile forces in the concrete, which will lead to cracking. So here, this figure shows in more detail the local area and the general area in a section, in a plan, sorry, and in a section, a sectional elevation of the slab. So you can see the local area is small, and that's where we saw the stress distribution of compression and tension, and then this is the local area, and that's here, it's the same thing, okay? So this is the depth of the member, it's H. So the extent of the general area is typically H to 1.5 H. Okay, so that's the extent of it. And then after that, the stress will be uniform and it will be taken properly by the slab. If we have that within the slab, okay, sometimes we have to do anchorage within the slab, and we talked about that in part one, then that is done in such way. So here we have, so from this side, due to that effect, we have 1H, and here we have 1H to 1.5H, as I mentioned before. So here we have um, uh, again, this shows the general zone and the local zone here that need to be considered, and the forces on the cables, and you can see the bearing plates which we have to design, and here we have the distribution of the forces, which is can be used for strata tie solution of the concrete section at the end of the member. Okay, so the local zone um, will experience, of course, high concrete stresses, and then, of course, tensile stresses. So whenever we have tension, then we have a problem with concrete, correct? So then we have to provide reinforcement at those locations, okay? So, and the bearing plates, of course, the bearing plates that we have here, where that's where the forces applied, of course, have to be designed properly, okay? So there are different types of bearing plates that can be used. One type is based on rational analysis. So basically, this is the type of plate that can be used, for these applications, and it worked without any issues, without any testing, of these plates from before, and the strength and all that stuff. And then there's the special bearing plates, which actually can transfer the load. It's known that based on previous data and tests, these plates can transfer the load properly without any local failures in there. So for the design, according to ACI, that the force that we need to design for here at the end, that we need to calculate, which will create compression and tension, is P sub PU, which is given by this equation. It's a function of the yield strength of the strands. It's a function of APS, the area of the strands. It's a function of, and of course, we have different factors. It's a function also of the ultimate strength of the strands, FPU. So everything is defined here, and then, of course, we have confinement reinforcement factor 0.85 is recommended here for 5. So that's where is this taken from ACI, okay, section 25.9. And then we have the general zone that has to be designed. So for that we have to consider P sub U under the local zone, and then the reinforcement shall be provided where required to resist the bursting and the spalling and the longitudinal edge tension forces induced by the anchorage device. Um, and according to the PTI, the design of the general zone is the responsibility of the design engineer. So this is something that you have to design it if you are designing the building. Uh, uh, Sometimes, of course, many cases the PT suppliers design that, at least how that it used to be before. But now with the more use of PT, engineers, actually the engineering record of the designers, do that. Okay. Now the general zone design can be done by finite element method, looking at the stresses at that area, using strut and tie models, also using the figure that we showed here. Okay, for those of you who are familiar with the strut and tie, so this the figure on the right. Okay, and then there's a simplified equation, simplified equations if they are applicable, and then we have an ACI procedure, for a simplified method that shows the piece of U that's applied. It shows the edge of the height of the edge of the edge anch, which is the height of the anchorage, which is typically the bearing plate. Then we see the E anch, that's the eccentricity, which is from the center of gravity of the member to the applied force. Okay, and then you can see the stress distribution, because this is not applied through the centroid of the member. It's up, so you can see the stress distribution is higher above. Okay, and then there is the H is the total depth of the member, and H/2 is the from the center of gravity to the edges of the member. So we can determine what is the tension force. Remember, so here at the beginning we have compression, then here we have high tension force. Okay, so that's the T burst that we can calculate from this given information. So it's not difficult to calculate using this simplified method. Okay, and that many people use that method actually. Okay, so then also, of course, minimum reinforcement for anchorage for monostrate tendons or smaller can be used. So there are different requirements, per ACI. For example, 2 horizontal number 4 bars shall be provided parallel to the slab edge, and they shall extend at least 6 inches either side of the outer edge of the anchors. So we have requirements like that. And then for each group of 6 or more anchors, hairpin bars or closed stirrups, can be used in that area. So we will see some details for that. So the hairpin bars or closed stirrups in that area to take that force. Now, these requirements can be waived if detailed analysis shows that this reinforcement is not required. So here you can see an example of the number 3 hairpin. So the total equal to the number of anchors plus 1. Okay, so that's given here, and then we have number 4 top and bottom. The ones that we talked about is shown here as well. Okay, and then you can see the anchorage and the other elements on the strands, for extension and for stressing and other details that also we showed from last time. Okay, here we have another example. For example, this is a fixed end anchorage. Okay, for a fixed end anchorage, so we can see the hairpins and the number 4 bars, top and bottom. Again, this is to prevent cracking at this area. We have to be careful because large force is applied at the ends here to apply the pre-tensioning force. I'm sorry, the post-tensioning force in the slab. Okay, so here we have also several requirements that are related to anchorage. For example, if we have monostrand, which is typically, we see that typically in slabs, but group of strands or multi-strand, typically we see it more in beams. Okay, and so that designed for groups of monostrand tendons in beams and girders. So that's what I was talking about. And then a design of general zones for the groups of monostrands in beams and girders shall meet requirements of 25.9.4. And the design of the anchorage zones for multi-strand tendons uh, shall meet the requirements of the same section as well. Okay, so basically calculating the loads for the local zone and the local zone and the general zone is explained and given in the simplified methods that are given by SEI. Okay, some people use finite element. I have seen that. Okay, but that depends on the computer programs, that they have. Okay, so here you have two examples with a step-by-step on how to calculate the bearing plate. Okay, the bearing plate here. Okay, everything is explained again, for just like we did in part one, just to cover everything on the design of PT slabs. um, I will leave this for you to go through them. They are step by step. Everything is explained with numbers. And then we have also the anchorage design for the general zone that we talked about. Here we have an example with also with numbers and step by step. Everything is given. Okay, then we just need to calculate the forces and then select the appropriate reinforcement, for that. Okay, so that's for the anchorage design. Then we'll talk about another serviceability criteria that's important for PT floors. Now, PT floors, one of the advantages for PT floors that we talked about last time is that we have thin slabs. So the result of PT floors is thin slabs compared to reinforced concrete slabs that have thick slabs relatively, if we are talking about the same span and the same material, right? Same concrete strength. So therefore, if we have thin slabs, then we may have vibration issues. So we have to be careful about that, and we have to check that. This is, of course, a serviceability criteria. It's not a strength criteria. But if the floor is bouncing, then it will not be serviceable. It's not comfortable for the occupants, especially in office buildings that are open, that has cubicles without full height partitions, right? So, so the vibration, of course, depends on the application that we use. So it could be um, a consequence of foot drop in residential or commercial floors, rhythmic vibration, dance floors, and sport events, vibration laboratories, manufacturing facilities, vibration due to vehicular traffic, due to operation of machinery, and then transient impulse due to earthquake, wind, or other impact loads. So the main focus here will be in the very common application, which is commercial or residential buildings, which is basically the foot drop of a walking occupant. So if we have to do something for rhythmic manufacturing, etc., sometimes you have to use like a more advanced techniques of analyzing concrete floors, which are available. So the analysis is not really difficult, but the criteria is different. So you have to look at the criteria for each of these categories. Okay. Now, one of the difficulties in the vibration design is the poor correlation between the outcome of the computation at the design stage and the response of the floor constructed. So that's one thing. So in numbers, everything may look perfect, but then okay, what do we have? What do we have in reality? So so in addition to the uncertainties inherent in the material, there is, of course, there are damping characteristics, boundary conditions. Is this fixed, or fixed pin, or pin? So we have to look at that. And the level of vibration perceived by individuals. Okay, there's a perception criteria for vibration, which we'll talk about. Um, and the vibration that's considered objectionable, and the force and frequency of the foot drop are all highly subjective to and prone to large vibrations. So, and I've seen that actually in actual floors where, I mean, just sitting in office buildings, when I was sitting in an office with cubicles, a large floor, it was a large floor, and then you could feel that when somebody is walking in the floor, especially if that guy was a big guy walking in the floor, and also if you are sitting in the middle of the floor rather than at the edge close to a beam or to a column, it makes a difference. Okay, so so the following factor must be identified at initiation of the design: the vibration source. Where is it coming from? The vibration transmission path, mass, stiffness, damping. So what could be the issue? Is it in the mass? Is it in the stiffness? Is it in the damping? Because this will lead to the solution. This will lead to the solution to increase the stiffness, or increase the mass, or increase the damping, or combination. It could be combination. Okay, and then how to determine the vibration characteristics of a floor at a design stage. So that's important. So coming with the characteristics that are needed for the vibration is important. And how to determine whether or not the vibration response is acceptable. Okay, so there's a criteria for that. So there are two methods employed, for this. There's the frequency tuning method, which sets the natural frequency of a floor system above frequencies susceptible to resonating when excited by a lower harmonic force by walking. Okay, and so basically setting the limit above what we need basically. And then there is the response calculation method, which is performance-based method, focuses on determining the likely vibration response of a floor under the application of a dynamic force of walking. So here we can present a simplified procedure, which is the response calculation method. Okay, so here where we have we can determine the response of the floor, and we can have an estimate of the damping, and we can have an initial estimate of the vibration, and then based on the criteria that then we have, and then this will tell us what we need to do in terms of adding stiffness, and in terms of adding a mass, etc. Okay. Excuse me. Now, vibration source from foot drop of walking individuals. This is one of the things that we need to. That's the source basically that we need to identify, and then walking rates that are above 2.5 hertz are uncommon. So typically we use that as an upper limit, and then for an open floor office, we can use an upper limit of 2.1 hertz. And again, this is based on based on like the walking rates. So the foot drop, they cannot be above 2.5 hertz, regardless. So that's why we can use that as an upper limit. So for low height partitioned office floors, we can use 1.8 because we have full partitions in an office like that. In an absence of more detailed information, we can use 2 hertz. Okay, so the force of vibration depends on the weight and the walking style of the individual. and is a fraction of the individual's weight. Okay, so here we have figure 1 that shows some guidelines on determining the fraction of the working person's weight, which is it's expressed in terms of the dynamic um, load factor, and is a function of uh, so this is here's figure 1. It's a dynamic load factor with as a function of the frequency. Okay, and that's the first harmonic of a working force. Okay, so the dynamic load factor that can be used in the analysis. And um, the transmission path of vibration. So the parameters governing the vibration response are the mass, modes of elasticity, damping, extent of cracking, if any. Okay, which luckily we will not have that in PT floors, but in some parts of the world, according to their codes, yes, it will become a parameter, and of course post tensioning. Okay, the mass. Okay, the mass is determined as the weight divided by the gravitational acceleration g. So we need to, determine that. The modulus of elasticity. We know how to calculate the modulus of elasticity of the floor of concrete, right? So now the elastic modulus for vibration is larger than the static modulus that we use, okay, E sub c, which we know, especially for high strength concrete. Therefore, it's recommended to use 25% higher modulus of elasticity than the static modulus of elasticity. Okay, so you find EC and then you multiply it by 1.25, so that's your E. Okay, and then of course damping. So there are different recommendations, for damping. Concrete typically is good in damping compared to steel floors, which also experience typically uh, vibration. So recommended values according to two different references, Allen and Murray, they recommended 2 to 3% for bare concrete floors and 5 to 8% with full height partitions. Okay, so that you can see the difference is significant. Okay, so there are damping factors suggested in the same reference are listed in table 1 here. Okay, and by Allen and Murray, we have these damping factors for um, different types of floors. So bare concrete floor, furnished low partitions, furnished high partition, and shopping malls. Okay, so we can use those. And then the extent, of cracking. This affects, of course, if cracking is there, then the moment of inertia is less. Then not all the concrete is effective. Then we may have an issue. Now we don't have that in PT floors. Okay, considering its very low stiffness, because the limits for tension in concrete floors is small. So even if there is a small crack, we can consider it as a gross cross section, as we talked about in deflection. So according to, for example, Eurocode 2, concrete, which is the concrete code, and most other major non-US codes, they permit a greater extent of cracking in PT floors. So there, deflection will become an issue and vibration will become an issue because they are considered as cracked floors. Okay. Okay, for post-tensioning, so somebody may look at this, I'll explain this from the figure here. So somebody may look at this as, okay, we have an applied force that is that's applied to the member. So you can see we have a PT force, and then this, which will create a camber or a deflection in the floor. It depends on the location of the PT force. So we will have a delta. Then we'll have a P delta. P times delta, that's a moment. So we have a P delta effect on locally on a member, okay? So how does that affect in vibration, for example? So now one thing that is important to understand here is, yes, this is an external this is an applied force to a member, and it will have a P delta effect. Okay, but for PT floors, because the post-tensioning force is applied to a concrete floor that will apply compression to the entire floor to prevent cracking of the concrete is not considered an internal, it's not considered as as an external force. It's considered as an internal force. Okay, an internal, like internal system. Okay, it's part of the system. The PT cables and the force is part of the system as a whole. It's not an applied force from outside. So that's why typically we don't consider that. Okay. Now the perception of vibration. So we have different criteria for perception of vibration. There's a criteria provided by here we're talking about the human perception criteria for floors. So there's a criteria providing by the Canadian Steel Code, and then there's another criteria by the Applied Technology Council, ATC 1999, and they address the same issue. So we have two figures here that show that. But the common consensus about among the investigators is that the humans are most sensitive to vibration of frequency between 4 to 5 hertz. Okay, 4 to 5 hertz. So larger accelerations can be tolerated at higher or lower frequencies. So here we have the figure from the Canadian code that um, shows the peak acceleration versus the frequency. So for different damping ratios, 3%, 6%, 12%. Okay, so we need to calculate this peak acceleration. Okay, and then for the frequency that also we calculate, we can see where we are with these criteria. Okay, and we will see how we calculate both. Okay, so this is the ATC figure that's used for human sensitivity to vertical vibrations. Okay, so here you can see, for example, for operating rooms and hospitals, that's stringent criteria, and then for offices, residence, and assembly halls, we have a different criteria. Okay, so determining the vibration characteristic requires finding the natural frequency of the floor and the peak acceleration, the associated peak acceleration. So how do we do that? So here we have so I'll go through the figures. So that depends on the boundary conditions. Okay, it depends on the boundary conditions whether we have simple supports or whether we have fixed supports. So we have to identify the boundary conditions that we have, and of course whether it's continuous beam or whether it's a simply supported beam. So that makes a difference. And then the parameters. So we have the parameters to use for the calculations are given here. So we have the first natural frequency of a rectangular slab panel is given in this equation. Okay, and then C is a function of the modulus of elasticity, the depth Poisson's ratio, G, and the applied load, actually the weight due to human activity on the floor. And then we have the other factors defined in tables as we see. So A is the span length in the X direction, and let's see here. Yeah, the rest is okay, clear. So here the natural frequency, that from physics, is omega divided by 2 pi, and then the circular natural frequency omega is calculated according to this equation. A and B are the dimensions of the panels of the slab, and then square root of D over M is given in this equation, which is the function of, which we talked about, function of modulus of elasticity, Poisson's ratio, thickness of the slab, G, and the load on the slab. Okay. So for example, for column supported structures, two-way actions resist the applied transverse loads, and the first mode of vibration can be that one of a one-way strip. So we can look at that first, and then look at the vibration, similar to what we do in deflection. Okay, so here we can continue here with calculating the natural frequency given the information here, and everything was defined before. So if we have a floor like this, so we can analyze this in some software. They will do the vibration analysis right now for concrete floors and also for steel floors. So we can see here, if you are looking at a single span, so we can see that the vibration is looked at here at this span in one direction. Okay, so you can see the mode of vibration that we have here. So one support here, a column, another column in the middle, and another column at the end. Okay, now the peak acceleration and acceptability criteria of vibration. So we need to calculate that. So we talked about the natural. We talked about the frequency f, and we talked about the peak acceleration. So how do we calculate that? This is calculated from the given equation here, okay, which depends on the gravitational acceleration, constant force representing the walking force, and then beta, which is the modal damping ratio, which we saw in table 1, and then W is the effective weight of the panel. So again, we talked about the panel, the mass, right? So is taken care of here, okay? And then Fn is the first natural frequency. Okay, so we can determine that based on this. So we calculate this, and then we have this figure, and then we compare with whatever limit that we have here. Okay, so in continuation, that's table 2, which has the constant phi here, which depends on the boundary conditions. So here we have A and B, and here we have restraints of strains, and then two sides are free, then we have a different value. So we need that in the natural frequency equation that we talked about, in the first natural frequency equation that we talked about at the beginning. Okay, and then we have also the K factor with that. So that's given also for us for offices, residences, small assemblies, assembly halls, and shopping malls. Okay, so that's for this. So now here we have also another detailed example of how to calculate the vibration, and then how you compare it with the criteria that's given. Okay, so everything is given here again, step by step. For the sake of time, you can go through the numbers. So this is the panel that we are checking. Typically we choose the largest bay. Okay, that would be the most critical for vibration. Okay, and then we put all the numbers based on what's given. Okay, and then we calculate here, for example, 9.10 hertz for the natural frequency. And we continue the calculations here, and then we calculate the minimum acceptable frequency is 4.3. So this is less than the first natural frequency that was calculated was 9.10, so that's okay. And then it continues here for, again, the peak acceleration. So AP over G is 0.1%. Then we can compare that with the ATC curve to see if this is within the limits. Okay, so as you can see here, that's what we checked here. So you can go through that, but here to show that's what we checked is less than what we have. So this is okay for vibration. If it comes above these, then if it's above these, then we have to do something: increase the mass, increase the stiffness, or increase the damping mechanism. Okay. Again, it continues here. So with this example. Okay. So here, for example, that's another check. Here it comes to be here. So if it's an operating room, of course it doesn't work. But if it's an office, residence, or an assembly hall, it works. Okay. Now, application of vibration-specific analytical tools. So there are, different ways of doing that. There's so you can do that in an Excel sheet, MathCAD sheet, based on the examples that you are given here. Okay, so you can develop that. It shows you can put the tables. You know how to develop Excel sheets maybe better than me, but this can be done easily because you don't have many a lot of calculations, for that. Or now, since we model floors in software, we can do that in many software using 3D modeling. Okay, for example, just to give you an example, Adapt Floor Pro. Adapt in general is a great software. Not yet do an advertisement for Adapt, but it's a great software to do PT design, and it's probably the first one that was available in the market years ago. It has a tool for vibration analysis, so that can be used to do that. And actually, the method that I explained before actually is what Adapt uses to calculate the vibration. So if you are using ADAPT, then and you need to verify your numbers, then you can check that based on the example that you have here. Okay. Good. So using finite element analysis, of course, for the floor, and then you can see here if you run vibration analysis, you can see that. I mean, you cannot get better than this, basically. So you analyze the entire floor, not only one panel, because it has continuity from this side, continuity from this side. The edge panel, for example, this one here, it does not have a continuity from this side. So you can see the first mode vibration, second mode vibration, third mode vibration, etc. Okay. So you can look at, if you want, you can look at a specific area for whatever reason. Why? Maybe this area in the floor will have, for example, an equipment. If it's a hospital building, maybe this is an operating room. Okay, so you can look at a specific area, look at the frequencies, and then compare them with the limit, that you have. Okay. Okay, so that's for vibration. Now we'll talk about the issues that you may see in PT floors, such as crack formation, um, deficient slab systems, inadequate design, inadequate detailing, poor workmanship. So again, these things are extremely important, and I'm sure all of you have heard about recent collapses of buildings, and there are many buildings that are not collapsed, but they have a lot of damage in them. We don't want any building to collapse. And hopefully not any building will collapse, and of course result in a tragedy and loss of life. But it's extremely important to watch for these things, cracks, which may lead to other things, um, to corrosion in the reinforcement. If there's a corrosion, of course, there is reduction in the rebar area, and if that's not maintained over time, disasters will happen. Disasters will happen, and that's, as you know, that's what happened recently, unfortunately. So, um, uh, so therefore, this could result in from an inadequate design from the beginning, inadequate detailing. Detailing is extremely important. So it's not only how many tendons or how many rebars we need, but how we detail that in the structure. And of course, one important thing is poor workmanship. Is what you have on the drawings, and you spend a lot of time designing and drawing and detailing and checking this, checking that, calculations, modeling. Has this been really executed? Is what you put in the drawings has been executed? That's extremely important. Okay, and There are many problems, of course, in buildings, and some buildings are in courts. I'm talking about not collapsed building. I'm talking about occupied buildings that have problems, and they are in courts, and due to issues. And in concrete buildings, most of these issues are a result of course, crack formation in the slab or in other elements. So one important thing is a restraint to shortening of the slab. So if the slab, of course, can move, expand, and contract, things are, of course, things can be controlled better. But if it's restrained, then if the slab wants to move, it cannot, then it will crack. Okay, so this is one of the things that is important to in detailing. So that things that have to be considered when we detail the structures. Uh, if it's the location of the strain to prevent the cracking, then we have to provide reinforcement. Okay. Now, for crack causes, BT floors tend to shorten, so there's elastic shortening, which we talked about in the losses, and then restrain volume changes, which include shrinkage, creep, and temperature effect. The walls and the columns restrain free movement of the slab. We talked about that. So detailing is important at the columns and the walls. Irregularities in slab geometry, such as opening or entered corners. So if there's a big opening, like for the stairs, for the elevator, for if it's a gallery, then these are openings within the floor. So how we detail around the openings? Okay, so that's important. So the slab tends to move. So if these corners, will have high stress concentration. Okay, and then they will result in cracks, of course. Now, tension developed in slabs due to, of course, restraints exceed tensile capacity of the concrete. So when it tries to move, okay, stresses are developed. Okay, tension stresses are developed. Then the slab tends to crack. So we have to have the proper detailing of reinforcement in that area, and we will talk about methods for that. So tension capacity is typically 250 to 300 psi of the concrete. So um, we have to watch for that limit and do things appropriately. The range for a contributing factor for different for slab shortening, we have shrinkage 50 to 65%, creep, elastic shortening 18 to 20%, temperature effect 15 to 20%. So as you can see, and these things will happen over time. Okay, these things will happen over time. Elastic shortening will happen at the beginning, but shrinkage, creep, and temperature effect. For example, in the Chicago area, of course, it depends. Creep, of course, depends on the weather, relative humidity, and things like that. Just an example, for the Chicago area, we have shrinkage of about 60%, creep and elastic shortening 20%, and temperature effect 20%. Okay. So this figure shows the percentage of final shrinkage and creep, and shortening over time. Okay, over time. So talking about 60%. Here, we have 60%, shortening, which will happen in 60 days. Okay, so that's just an example for that, and this is taken from the PCI design handbook. Okay, so in PT floors, PT cracks were fewer. They are in fewer numbers. They are wider and deeper. They're spaced. I think actually I can show you those. In they are typically longer, they are wider, um, they are deeper. Okay, but in mild steel floors, they are larger numbers, they are shallower. Crack spacing is closer. Cracks are shorter in length. So everything is summarized actually in this figure. So in the left hand side, we have the PT floor, so you can see the cracks, how they are developed here. So they are wider, they are longer, they are deeper. Okay. In the right hand side, in the typical reinforced concrete floors, we have typically they are shorter, they are shallower, they are closely spaced. Okay, So that's the nature of the crack. So what can we do for crack mitigation? So planning the layout and the restraining members, like the walls mainly, the shear walls, the core for elevator and stairs, plan that, and the columns, structural separation, and then the pull strips and construction joints, released connections, and then addition and improved layout of mild steel also to mitigate the crack formation, and improved layout of the tendons. So we will see that. So what we will do now, we will go at images that will explain what we are talking about here. So for example, here, this figure shows the favorable arrangement of walls. Okay, favorable arrangement of walls. So here we have, for example, when the core wall in the middle, okay, the core wall in the middle. So you can see these parts here. You know, we have columns here, but we don't have a rigid element to restrain them. Okay, to restrain them. Here we have, for example, for walls, for like not long walls, they are arranged in such way. So this wall is in the middle. So this side is free from here. This side is free from here. Relatively, the column cannot restrain like the wall. Same thing here, free from this side, free from this side. The same thing here, same thing there. Now for the unfavorable arrangement is this. So here, as you can see, this side is restrained by this wall and that wall. Here's the same thing, restrained by two walls, restrained by two walls. Here we have also, we have like a larger area, okay, that is restrained in both sides. Okay, this is not like that. Here we don't have, we have the walls and that's it. Here you have columns in between also. So it's restrained in both ways, and it cover like maybe half or more than half of the floor area. So that's also an unfavorable. So that's the layout. That's the layout and the planning of the floors. So that will help in crack mitigation. Structural separation and expansion joints. Of course, this is introducing separation joints between whenever you have irregularity in the structure. That's very important. And introducing structural separations and expansion joints, which we may require double columns, sometimes double walls, may prevent collapse of large buildings. If one element of the building, so let's here look at an example here. So here we have, for example, this building. It's one floor. It's, let's say this is L-shaped building. If you live in that building, you don't feel the difference, okay? But structurally here, we have structural separation. Okay? We have a wall here, we have a wall here. So this could be in a unit where you have a door here, so you will walk from one side to the other without feeling that there's a joint here. So so this allows each element to move separately. Okay, each element to move separately. And if failure would happen for one part, let's say the smaller one, for whatever reason, it does not affect this one. It will not drag with it another part of the building. Okay, and then you saw what happened recently, right, in the building that collapsed. So these things are important, and they help. So this is how this is shown. Again, you don't feel it if you live in the building, but that's how it is. So that's a structural separation. Um, Here, the same thing. So we have openings, for the elevators, for the elevator core. So we have slab isolation joints are provided here. Okay, and then we have pour strips or the closure strip. So here you are given, the information about what's typically used, but we can look at that, in the figure here. So here, you have this part of the PT, you have this part of the PT, you have this part of concrete here, and then you have this. This is the reinforcement here. So this part was left without, of course, the PT. Okay, this part was left without the PT. So So that's called the pour strip. So, and we use that also to apply the pre-stressing of the slab. Okay, we saw pictures before about that, and I think I have more, coming on this. Okay, so how wide is this? What type of reinforcement? All that stuff that's given in the previous slide. You can take a look at that. So typically here mild reinforcement that is provided. So here's an example for that. Okay, so we apply the pre-stressing from this location, but this is made of just typical reinforced concrete. So here's another detail that shows that with the rebar. So from this side is PT, from this side is a PT, this is RC, reinforced concrete, and that's how we detail it. Okay, that's a typical push step. So and then we have construction joints, and the same thing. Construction joints, help of course in uh, eliminating the cracks in the slab. So where do we provide construction joints? So typically, if the length of the slab is less than 250 feet, then no pour strips or separation is needed. If it's between 250 and 375, then provide one centrally located pour strip. And if it's more than 375, then we need to provide a separation such as expansion joints. So these are rules of thumb that can be used, for the slab that you are designing. So this is shown here. This is shown here, where here, for example, we have a slab like this, okay, and then you can see we have. So here we have like 90 feet, and then we have this bay here. This is like a shorter span, so we can have the pour strip here in this shorter span, okay, because the of course the force, of course the effect of the force will be high here because the span is shorter, because it has to be up here and then down again here. So typically when you go from a large span to a shorter span, you have to look at the forces carefully in the shorter span. So we can have that here, and then we can have the stressing at that location, okay, and then so this is more in the center, this is more to the left, and this is a wider, pour strip that can be provided if you have equal spans. Okay. Then released connections. What is released connections? Of course, they help release any stresses there, and of course will prevent the restraint. So what are these? We'll look at the details. Okay, so here you have, for example, a dowel. Here you have another dowel. Of course, this is a void around bar to be grouted later. So that's a grout. So basically, the release is done by something like this, and not into the concrete, so it will not be restrained. And here you have like a smooth trowel, which is a finished layer of visqueen to act as a bond breaker. Okay, so that's a wall slab release detail. We have other examples for this that are shown here, and then we have another example that that is shown here between the wall and the slab. And here we have non-shrink grout, and here we have that column release detail here. Okay, and then we have that also here. That's a column release detail. Oh, sorry, wall release detail. Okay, and these are actual pictures of how we do that basically in practice. You can see the concrete is not there, so we can provide a column release detail. Okay, so you can see that here. And then additional improved reinforcement. So basically the steel quantity that can be placed parallel to a rigidly connected wall for a distance of 1/3 of the transverse span. Okay, so 0.005 times the area of the concrete. So whatever width we have times the thickness of the slab, then we have to, for example, if it's a 12-inch, if it's um, we have an 8-inch slab, and then for example for per foot, then we can have this area, and then this area will be If we provide number 4 at 16.5, then we will achieve that. Okay. Now, here, for example, at an exterior walls, provide details like this, provide reinforcement like that, okay, to prevent, cracking. Provide reinforcement like this. So you have two number 5 top and bottom. Here we have number 4 at 12, like this, top and bottom, and then also we can use something like this, okay, if it's an interior. So we can have reinforcement, like that, and that of course will help in preventing cracks at that area. Okay. And then for the PT, how can we improve the layout of the tendons? So instead of having the tendons stop like this here at the opening, then we don't stop them like that. We have them continue like this from this side. We have them continue like this from this side, so that cracking do not develop at the end of the member, okay, or at the at the corner of the opening. So that's important in detailing. Again, detailing, as you can see, these are all detailing issues to prevent cracks. Nothing to do with the design. The design you did, how many, the number of tendons you need, the spacing, the what mild reinforcement you need. But now everything depends on the detailing. Okay. So some of the points to consider, like shortening cranks are frequent in post tensioning close to the walls and columns. Shortening cranks do not normally impair structural integrity of the slab. And then impairment, exposure of rebar and PT to corrosion elements, leakage and aesthetics. Of course, if we have cracks, then we have issues. So we have to watch for that. For PT, slabs use various crack mitigation details, like the ones that we talked about. Okay. Okay, a crack treatment. So if we have cracks, so how do we treat that? So if the slab is not expected to move, then we use epoxy injection. Okay. If the slab is expected to move, okay, then we use flexible sealant. Okay. Okay, so that's for causes of cracks, how we can deal with that in details, and then how we can, and then if we have cracks, how we can mitigate that. Okay, now we'll talk about some of the field issues. Okay, some of the things that we've been talking about, cracking issues and field issues, and we talked about execution of your drawings in the field, is that accurate or not. So what things to look for basically, and some of the field issues that you have to see. So do the PT profiles match the control points given in the drawings? So the profile, the tendons go in profiles. Okay, so we set the profile for that. We put in the drawing, how much from the top, how much from the bottom. So do they match? That has to be checked. So we need to measure high point, low point, and those are given and should be within SEI and PTI tolerances, and these tolerances are given here. Okay, for different thicknesses of the slab. Okay. See if the profile is a smooth parabolic profile without abrupt changes or reverse curvatures. Check if the low points at mid spans in the interior spans and slightly off in the exterior span, 0.5 to 0.45 L in the exteriors, from the exterior support. So, you need to look for that, because these are in PT, in pre-stress, these are controlled, these are done in the factory, and we put the tendon before the concrete. But in PT, then this is like reinforcement. Everything is done. The cables are thrown on the formwork, and then the post-tensioning after we cast the concrete is done. So we have to make sure that things are in place, and also don't, of course, So when we apply the PT force, everything is in place. Check layering of PT and mild steel reinforcement. So where should be the steel, where should be the PT? Okay. And then, does this match, the drawings or not? Is the mild reinforcement, for example, at the column slab connection above or below? So we need to look at that. So here you have some of the, so you have here, typically the mild reinforcement is over the PT. So here we can see, so we need to look for the right arrangement and make sure it's done properly. Okay. So here you can see, for example, the PT tendons, you can see the rebars on top of that. And then here you see these are the headed studs. These are the headed studs for the punching shear. Okay, so that's another. So this is not difficult to uh, to into to inspect. Um, so you can see that. You can see the profiles at the column strip and the middle strip and all that stuff. Okay, this is at the end joint. So you can see the cables where they come, for anchorage at the end, and then you can see the the reinforcement above that. Okay. And this is, for example, a plan of a two-way slab showing for example, a group of tendons, showing the mild steel, reinforcement, showing the rebar, spacing here, and then this is the banded tendons, which are in the different direction. So we have distributed tendons, and then we have abandoned tendons. I mean, look at the example. There's a full example of a two-way slab that you have in part one. So you would know exactly what these things are. Okay, that's a section, basically showing showing the tendons and showing the rebars. Okay. Okay, and then prior to concrete placement, also review the sleeves, the holes in the anchorage zone. Okay, so we need to make sure that those are reviewed and appropriate. So we can look here at the figure which explains the previous slides. So here we have, for example, these are the this is the this is the tendon here. Here we have some holes and openings, within the slab. Then, okay, at 45 degrees, where do we go? A large force will be applied here. Where would that be? Where would that opening be? Okay, where would that sleeve, be here? So here we have to be careful and then provide whatever steel is needed. Whatever steel is needed. So here, for example, goes through an opening. So provide steel pipe insert scheduled 40 for the thickness when slab penetration is within 45-degree lines from a tendon anchorage. Okay, so we have to do something here. Okay, and of course, and here you can see, the tendons, of course, in the outside. Okay, eventually this has to be, of course, closed. Okay, here we have some also tendons, so some of the issues here that need to be looked at. Okay, so why do we have that? Why and of course this shouldn't be left like this because it will, of course, cause corrosions. Observe if couplers are adequately used. So if couplers uh, are used, then we have to make sure that they are used properly. Exposed or damaged strand. Okay, exposed or damaged strand. So if we have something like that, what does that mean? Okay, when we design and check stresses, just like we said in part one, we have to be accurate because concrete stresses may be exceeded. Okay, and we calculate that based on the PT force, whatever force is applied. Okay, so here you have maybe one strand. Here this is 7-wire strand, right? 7-wire strand. So if one wire is cut or two wires are cut, so what do we do? Okay, so we don't have to replace it maybe, but we have to apply the force that's required. So maybe we apply more force to the remaining 5, okay, to take that force, okay, to apply the force that is required. Okay, so instead of being applied to 7, they will be applied to 5. So we increase the force so the 5 can have the same force. Okay, of course that's repair at those locations, for the strands, and then check horizontal curvature. Okay, horizontal curvature, the slope exceeds 1 to 12, then provide number 3 at 12 bars. And then if the slope exceeds 1 to 6, then, revise the layout of the tendon. And I'll show you what we are, talking about here. So tendon adjustment, and then chairs and supports, of course, they have to be, provided at a maximum of 4 feet. Support bars over chairs shall be minimum number 4 bars. Okay, so here we're talking about the curvature. See, so that's what we're talking about. It's talking about the curvature in the tendons, and we have other examples. So here around the openings, So if the slope is greater than 1 to 12, then we have to provide, these number 3 hairpins bars. So if this is the maximum horizontal slope is 1 to 6 here, okay, and then here you can see the corner reinforcement, that the diagonal bars that we talked about, and also this has to continue minimum 24-inch straight, behind this point. Okay, this is for the curvature. Okay, so for a curvature that's more than 1 to 12, then we have to provide these. Okay, so here you can see this tendon, the green one, is coming from here, and then it starts to have a curvature like that. So here you can see what the hairpin bars. Okay, this is the same thing here. See? Okay, see that? So that's the same thing that we've been talking about. Okay, here's the same thing, for example, at the curvature here, so we can see the hairpin bars there. And then after the concrete placement, okay, honeycombing, this is normal in concrete, so we have to uh, look, for that before the tendons are stressed. Remove all loose material, patch with high strength, non-shrink concrete repair mix. Stress only after concrete has reached the required strength. So if there are area concrete missing, honeycombing in the concrete, then we have to patch that with high strength concrete mix, wait until it achieves its strength, and then apply the pre-stressing. Okay, blowouts. This is the rupture of the concrete here. So when we apply the pre-stressing, so as we said last time, the pre-stressing force is applied after the concrete reaches 3,000 psi of its concrete, okay, of its strength. So and then when we apply the force, okay, do we have concrete blowouts like that? Then yeah, we have to. So that's after the concrete. So we have to take care of that. We have to repair, these locations. Okay, so this happens actually, so we have to repair these after. And then out of range elongation. So when we apply the pre-stressing, we have to, of course, look at the record, the elongation record. So we apply force, so we have the tendons, of course, will elongate. So that is measured actually. That is measured. Okay, that is measured. So we have to, we have a range for that. Okay, we have a range for that, which should be specified, on the drawings. So we have to make sure that they are within the range, not outside the range, and then look at the force that's within the member. So that's how we measure that. Okay, as you can see, it has been stretched. So this is the elongation that we got, after applying the pre-stressing force. Okay, now future openings. This is very tricky in in PT floors. Okay, so we have to be careful about opening openings in the floors and doing repairs. We have to know where we can have openings. So if there's a future opening that is planned by the architect, and then of course the engineer will design based on that. Like he or she will design like the tendons to go around that area. Okay, and then that area will be just reinforced concrete. So if they cut that opening, then we know that the rebar is there. And of course, they have to know the exact location of the opening and the tendons as well. So they don't cut the tendons as well, which may lead to a disaster in PT. Okay, and we talked about that. Okay, so and these days, of course, with the increased use of PT, usually the engineers, provide the layout of the tendons, so mistakes will not happen in the case of for example, drilling something or having future opening or even hanging things, from the slab. Okay, and then of course anchors into the concrete for whatever reason, used to hang something from the concrete. This is um of course could be done in different ways. If the layout of the PT is there, then you know what to do. Or there could be inserts within the floor. So when they cast the floor, they can have inserts for certain things to hang. Okay, but this has to be studied in detail, like architecturally. So those can be used after the building is occupied. Okay, and then strand breakage. So we talk about this. So either strand damaged or breakage, then we have to apply. So we have 7 wires. Then we have to apply a force that can be taken by the 6 wires if it's broken, or by 5 wires if 2 are broken. Okay, so we have to increase the PT force. Okay, concrete strength at stressing minimum of 3000 psi. We talked about in the last time. Tendons to be stressed within 72 hours of concrete placement to avoid plastic shrinkage. Okay, so we have to have that strength 3000 psi achieved, before the 72 hours, and then minimum concrete strength shall be established by cylinder breaks. That is that's taking at the time of casting, of course, and then tested in the lab. Okay, stressing sequence. So for one-way slab and beams, and stress continuous uniform slab tendons first, then stress temperature tendons, then stress beam tendons, then stress add tendons. Okay, any additional that are added. Okay, for two-way slab, stress continuous uniform slab tendons first, then stress banded tendons, then stress added distributed tendons, then stress added tendons in banded sections, in the banded direction, and then in general, the uniform tendons are stressed before the banded or beam tendons. Okay, so this one shows the banded tendons that we talked about last time, which are concentrated at the column strips, and then in the other direction we have the distributed tendons. Okay. Um, core drilling. So the same thing. Any core drilling within the slab has to be checked with the engineer of record, and the engineer of record will give the direction on how to do that. Okay. So, for example, the tendons are banded in one direction and spaced apart 3 feet to 5 feet typically in a uniform direction. So this gives some idea of how this can be, of where cores can be taken, but again, it has to be consulted with the structural engineer, the engineer of record. So power driven fastener, the same thing. So here we have to be careful about the layout and the location of the tendon. So if it's in the middle of the span, we know the tendons will be at the bottom, so we have to be careful. So we can put things on top of the slab if needed. If it's close to the column, we know the tendons will be at the top. Okay, then you can maybe drill at the bottom of the floor. Okay, so this all depends on the layout of the tendons, and of course have to consult with the engineer of record. And then use of embeds and use of drilled anchors, we talked about that. So those can be, some inserts and embeds can be done before, and this is done typically. It can be before casting the concrete. Okay. And then tendon grouping, banded direction, maximum 5 tendons allowed per group unless approved by the engineer of record. And then uniform direction, typically 2 tendons are spaced at spacing subjected to minimum 8T or 5T. I think we have details from the previous, from the first part that talk about, also show these things. And then tendon tails. These shall not be cut until all tendons are stressed elongations measured and the engineer of record approves that. For encapsulated systems, the tendons, we talked about encapsulated systems last time. The tendon ends shall be protected with grease-filled watertight cap, and we showed that as well. Okay. So here you can see, look at some of the inserts. You see some of the inserts here. So you have a couple of studs in the plate. So you can see where they are put, right? So when they cast the floor, you should be able to see these from the bottom of the floor, and then you can use it for whatever application. Hang an equipment from the slab, so it can be welded or connected to these plates. Shoring. Shoring is another thing that we have to specify. It may be removed when all tendons are satisfactorily stressed and the engineer figured approved that. Exceptions will be in staged pre-stressing, such as transfer girder. So we talked about that last time. If you have transfer girder, then we do the pre-stressing in stages. For example, transfer girder of a column in a multi-story building. As we increase in construction of more floors above, we apply more pre-stressing. Okay, because the pre-stressing force is a function of the load that's on it. So these things have to be studied. What shoring should be there and what shoring can be removed. Tendon stressing at previously cast walls. So if there's a wall that was cast from before, and then what can we do for tendon stressing, then we can look at these details. So here, for example, we have dead end anchorage cast into the wall. Okay, so that's a previously cast wall. So, but we have a dead end anchorage that's cast in the wall. And here we have, for example, a dead end anchorage that is placed here, but that pre-stressing would be from the other end. Okay, so this can be done like this, and you can see the reinforcement that's provided. Here we can have, as you can see, this is the stressing pocket. It's at the end of the wall that is existing from before, or that was maybe not existing but cast before the slab. It could be done here. This is concrete poured. This concrete is poured later. Okay, and that's where the stressing is done. Okay, and then you have these are coming out. These rebars coming out of the wall at the time of casting the wall, and then also could be done something like this here. So you can have the stressing pocket could be done here. So we have those are coming out of the wall, and then the proper reinforcement can be done here. Okay, and or something like that. So this is similar, but from both ends. Okay, here we'll have just like for here we'll have stressing pockets, right? Stressing pockets at these ends, so we can apply the pre-stressing either from this side or from this side. Okay, and that's it. Thank you very much for listening. If there are any questions, so we're almost 2 hours as planned. If there are any questions, I'll be glad to answer. Of course, you can email me as well. Okay, what PT software you recommend? Um, I I explored. Look, I mean, um, I would say um, Risa, Risa, which is ADAPT now. Risa ADAPT. So ADAPT was a company by itself, and then Risa bought ADAPT. So there's ADAPT PT for ADAPT PT RC, which is for like designing segment by segment of PT. It's easy to use. There is um, there's ADAPT Builder, or ADAPT Builder, which you can model an entire building, and then take a slab and also design that slab for PT4s. It's 3D and relatively new. I've used RAM concept a lot from Bentley, so that's good. I have good experience with that. And I know Safe also has. I have not used it, but it has PT. But mostly I used Adapt and RAM concept. Um, so um, which one is better? Maybe I would say maybe Adapt. So other questions? Okay. If there are no questions, I guess we can conclude now. And if you have any questions, you can email me. Okay, what software would be best for PT beam and joist system? Probably, yeah, for a joist system, probably adapt would be more appropriate um, than the others. Other questions? Okay, feel free to email me anytime about any. So you should have between part one and part two, you should have about 469 slides. That has a lot of information, and from design, from construction issues, from as you noticed, serviceability, deflection, vibration. Um, you can go over it. It's a lot of material. Any question, feel free to reach out, and I'll be glad to help. Okay, thank you, and have a great weekend.